Good afternoon, ladies and gentlemen. We are going to be continuing our discussion on reaction rates and equilibrium. So far, we are in chapter 18. So far, you have looked at the definition of a reaction rate. You looked at the things that affect reaction rate, such as catalyst and temperature and surface area. And you've also looked at the different ways in which a reaction can run. So you've had to calculate your activation energy for a forward reaction being something that runs from a reaction that runs from left to the right. Okay, and then you also looked at a reversed reaction, the reactions that run backwards. Okay. Today we're going to be looking at what's called a reversible reaction, and that's a reaction that can run both ways at the same time. Okay, so this is actually coming out of section 18.2 in your textbook. There is in Google Classroom 2 documents that I'm going to put in. One is a set of notes which you need to copy into your notebook, okay, or you can print out the sheet and fill in. Okay, that it's a two-sided document or 2 pages. So either print the 2 pages and fill them in, or what you can do is just write these notes as we're going over them in your notebook on the appropriate page, and all those instructions will be in Google Classroom. There is also an assignment, a worksheet that will follow, and that is also 2 pages long. You can again print that out, or you can just draw it out in your notebook on the assigned page and complete it that way. And then what you're going to need to do is you're going to need to, whatever form you're doing it in, you're going to need to take pictures of your work and submit them in Google Classroom for credit. Please make sure your pictures are clear, that I can actually read your writing. Okay, if I cannot read what is on the papers, then you will not get credit. So please be careful of the shots that you take. You do not need to put them into a Google document. You can just upload your images. If you put them in a Google document, please make sure that they are oriented correctly and that they are large enough for me to see, and I don't have to go in and change the size of it. Okay, so I'm going to go ahead and switch screens, all right, so you can see what's going on, what document I'm talking about. All right, so these are the notes that you will be filling in. I'll be switching to the PowerPoint and might be going back and forth between this and the PowerPoint so I can show you what you need to fill in. But the title of the notes is Equilibrium, Le Chatelier's Principle. Okay, and again, there are 2 sides to this document. Okay, so this will be assigned to 1 page in your notebook. Check Google Classroom to find out what page it goes on, or check the table of contents that will be updated. And then the second thing that you will need to print out or put in your notebook is the assignment that is going to go along with this. You're going to have several assignments that are for Le Chatelier's Principle, and there will be a quiz on this. So please make sure you're doing this and you're familiar with it. Ask questions, and questions my way if you have any, because there will be a quiz coming up. All right, so again, this is the assignment. There are 2 sides to this, so you have actually 3 charts that you will be working with. Okay, so today again, Le Chatelier, we're looking at equilibrium. Okay, so balancing out the reaction. So this is the beginning of the notes. So students know how to use Le Chatelier's principle to predict the effect of changes in concentration, temperature, and pressure. So basically, as the reaction is going to run, depending on what is happening, okay, are you adding more material? Are you changing the temperature? Does the pressure change? All these things are going to affect which way a reaction will run. Okay, so remember, we're looking at reversible reactions, reactions that can run forward and backwards at the same time, forward and reverse reactions happening at the same time. Okay, so what happens is the speed of those reactions can change depending on what is changing, your concentration, your temperature, and your pressure. Second thing that you are to know as students know equilibrium. Equilibrium being that balance is established when forward and reverse reaction rates are equal, meaning the speed at which your forward reaction is running has got to be equal to the speed of your reverse reaction in order for this equation, for this reaction to be in equilibrium. All right, so what is a reversible reaction? Okay, reversible reaction is a chemical reaction in which the products can react to reform the reactants. Again, a chemical reaction, reversible reaction is a chemical reaction in which the products can react to reform the reactants. Okay, so one example here, the one that's given, actually, let me back up and I'm going to give you an example. So reversible reaction is a chemical reaction in which the products can react to reform the reactant. So for example, let's take it away from chemistry, but let's say that I am working with bicycles, all right? And I have all these bicycle parts that are sitting in the classroom. You've got your pedals, you've got your chains, you've got your handlebars, your seats, your frames, all of these, just a bunch of material, all right? And you can count them all out. Now, when you have a bunch of bicycle parts, the product would be taking those parts and then making a bicycle, okay? So taking those parts, the bicycle parts that are all separated, putting them together to form a bicycle. So your reactants would be the bicycle parts, your products would be the bicycles, the ones that are all put together. Okay, so in this forward reaction moving one way, what happens to the number of bicycle parts that I have available as I am making bicycles, as I'm putting them together to make bicycles? What happens to the number of loose bicycle parts that I have available? That number is going to get reduced because I'm using them up to make the bicycles or the product. So what happens in a forward reaction, your reactants get used up and your products are increasing, they're being made. So reactants are decreasing where your products are increasing, okay? The reverse reaction would be the bicycle being taken apart. So taking the product and breaking it down to form more reactants, all right? So reversible reaction in which it's happening both ways is I could be putting bicycles together using up the bicycle parts of these reactants to make bicycles, but then someone else on the other side is taking the bicycles that I'm putting together and they are taking them apart and putting those parts back over in the beginning, okay? So that's what happens with a reversible reaction. It is a reaction that can go both ways, okay? And it can happen at the same time. The rates can vary though, all right? So I could be making bicycles faster than someone is breaking them down. Someone could be breaking them down faster than I'm putting them together. Or what happens is they're happening at the same rate. Okay, so what happens is as I am making the bicycles, someone is taking them apart. So what it looks like is the number of bicycle parts doesn't really look like it's changing, and the number of bicycles produced doesn't really look like it's changing, okay, even though stuff is continuing to happen. All right, and that is called equilibrium. So in chemical equilibrium, when the rate of the forward reaction, when the rate of the forward reaction equals the rate of the reverse reaction, and the concentration of the products and the reactants remains unchanged. So let's say that there are 30 bicycle parts, all right? And there is one bike that is already made on the product side. As I am taking these separated parts and making more bicycles, someone is taking the bicycles that are made and they're breaking them down. So even after time has passed, let's say 20 minutes, 30 minutes, an hour has passed, if you look at how many reactants you have and how many products you have, you would still have 30 reactants and one product. You started out with 30 bicycle parts and you already had one bicycle on the product side. And even though things are being made and things are being broken down, overall, it looks like nothing's happening. Okay, so the numbers stay the same in chemical equilibrium, because what happens is as quickly as I'm putting bikes together, someone is breaking them down at the same rate. So the speed at which they're happening has got to be the same. The example that is given is you have 2 molecules of mercury oxide, HGO, and it is in solid form. And then what happens is you see the arrow. You have arrow going both ways, one moving to the right and one moving to the left. Okay, this right here. That shows when you see 2 arrows like that, okay? It may be one arrow that has 2 tips on it, okay? Or it could be like this, all right? So there's different ways that they can make the arrows. But if you see the arrow tips moving in two directions, that means it is a reversible reaction, okay? It's moving, it can move in both directions, all right? So we have 2 HGO yields 2 HGL, Hg, 2 molecules or 2 atoms of mercury that are in liquid form, plus your oxygen, which is a gas, okay? Make sure to write that equation down. That should be right above the statement, which you're not able to see. It says arrows going both directions indicates equilibrium in a chemical equation, and that's written at the bottom of your notes. So right above that, please make sure you write down that equation. Chatelier's principle states when a system at equilibrium is placed under stress, the system will undergo a change in such a way as to relieve that stress. So what happens is if you have a reaction, okay, reversible reaction that is in equilibrium, if something happens, let's say you add more reactants, if you remove product, if you change the temperature, if you increase the pressure or decrease the pressure, you're putting the system under what's called stress. And as you are doing this, what happens is it can throw it out of equilibrium. So something can happen to the reaction, something is going to take place in order to try to bring it back into equilibrium. So when you take something away from a system at equilibrium, the system shifts in such a way as to replace what you've taken away. When you add something to a system at equilibrium, the system shifts in such a way as to use up what you've added. Okay, so the first example here is, it says a closed container of ice and water are at equilibrium and the temperature is raised. So you have ice plus energy. And again, this is another way to represent the arrows. You can join these arrows and have them just have one line with 2 tips on it, or you can draw the arrow as it was in the other example where you have one arrow above the other, okay, both pointing in different directions. So ice plus energy yields water. The ice plus the energy, they are the reactants in this equation. The water, being on the right side, is the product in this equation, okay? So it says what happens is we are going to change the temperature is raised. So which variable in this equation would be associated with temperature? Would it be ice? Would it be energy? Would it be water? Temperature is a measure of the average kinetic energy, right? So if the temperature is being raised, the energy here is what is being affected, all right? And that is being raised. So you can put an arrow over that to show that that has increased. Now what happens is because you have something that has changed in here, you're putting a stress on the system, that is going to throw this out of equilibrium. So whereas before ice and energy were being converted to water and water was being converted back into ice and energy at the same rate, and these are in equilibrium, now that you have put the stress on the system, it's not going to be in equilibrium again. It's something is going to have to change. Something's going to have to take place in order to bring this equation back into equilibrium where the rates of the forward reaction and the rate of the reverse reaction are equal, okay, to each other again. Because this stress is going to throw them out of equilibrium. So the rates at which the forward and reverse reaction happen will not be the same, okay? So what is going to happen in order to bring this back into equilibrium? I'm going to switch out of the screen real quick so I can give you an example. So we have, let me write this down first. You have ice plus energy produces water, reversible reaction. Okay, so I have this equation written down. And this is temperatures increase, which is again affecting the energy. Okay, all right, now I want you to think of it this way. Let's say that we have a container, and you can do this for every single example, just gives you a visual on this. So let's say that we have a container of water. Okay, and one side is going to represent the reactants, which is your ice and energy, and one side is going to represent the water. So let's say what happens is right here, I'm going to split this container in half, right where the yield sign is, your arrow. Okay, and again, this represents your reactants, which is your ice and energy in this case. And then to the right, we have the product, which is the water. Now, currently what happens, we're going to just treat this as a container of water, and there's a screen that separates them, okay? Now, what happens is right now, initially when we started this, before the energy was changed, the temperature was raised, the water level was the same on both sides. Okay, so let's pretend that there is a block here, piece of wood or something, some separation, some boundary that keeps the water from mixing, okay? When I increase the temperature, that means the reactant side up has increased. So I have more water on this side. This side is higher. Okay, there's more water over on this side than there is on this side. Okay, this goes all the way up here, whereas this is just here. This water over here, water level is higher because I increased the temperature. So I made the reactant side higher than the product side. So if this was a solid screen, let's say that I have a porous screen, something that water is able to flow through that's there. I remove the solid screen and then the water can flow. Water can move from this side to the right, or water can flow from the right side to the left. If this side is higher, has more water, and I remove the barrier, which way is the water going to flow? Is the water going to move to the right side, or is this water on the right side going to move into the left side? Think about a waterfall. Does water flow from the highest point to the lowest point, or does it go from the lowest point to the highest point? Okay, water is going to fall. It's going to go from the highest point to the lowest point. So what that is going to do is cause the water to move from the left to the right, okay? That's called a shift, okay? And by doing so, the water is going to flow into this until this is in equilibrium again. And that is what's going to happen in your chemical reaction. So temperature is increased, which means the energy is up. The equilibrium of the system shifts to the right. Okay, there's extra on the left side, on the reactant side. So you have stuff that is going to move to the right side. It's going to shift to the right. The equation is going to, the reaction is going to shift to the right in order to bring this back into equilibrium. What that means when we say that it is shifting to the right, that means for the time being, your forward reactions are going to be running faster than your reverse reactions. Your forward reactions will happen faster than the reverse reaction is happening. Ice and energy will be converted into water faster than water is being converted back into ice and energy. Okay? Next example. A closed container of N2O4 and NO2 at equilibrium. NO2 is added to the container. All right, so writing out your equation, it's going to look like this. It says N2O4 and NO2 are at equilibrium. And then NO2 is added to the container. So what arrow are you going to add to this? Make sure you're adding all the arrows. Everything that appears in here in the video needs to be in your notes that you're submitting, so I can see how you are getting to the answer. Okay, remember the G's after this just stands for the states of matter. So this N2O4 is in the gas phase. NO2 is also in the gas phase. All right, it says NO2 is added to container, which is this. So what are we going to do with that? Is there going to be an arrow up over the NO2, or is there going to be an arrow down? NO2 is added to the container. Arrow up. Okay, so go back to your water example. Sorry, wrong one. Okay, let's go back to this example. So this was arrow up here. Going to make another container. Okay, this side represents products, your NO2. This side represents your reactants, which is your N2O4 and energy. This side has increased. So that means the water on that side is higher than the water on the product side. So again, if you remove the partition, which way will the water flow in order to get this back into equilibrium? This side is higher, think waterfall. So that means the water is going to flow into this area. It's going to flow towards the reactant. So it's going to shift left. Equilibrium of the system shifts to the left to use up the added NO2. So once again, you may want to write this down. What does that mean when we say it shifts left? Okay, shift left is a reverse reaction. So shift left means your reverse reaction is going to be happening faster than your forward reaction. NO2 will break down into N2O4 plus energy faster than N2O4 plus energy is being converted into the NO2. The reverse reaction will be happening faster than the forward reaction. Example 3. A closed container of water and its vapor are at equilibrium. Vapor is removed. You're taking it out of the system. Here's your equation. Make sure to write it down. Vapor is removed. So find the vapor in the equation. You're going to have arrow up or arrow down over it. Be arrow down. Go ahead and draw your water container underneath. So since the water vapor side is down, that means your water level on the product side is going to be lower. The water plus the energy is going to be higher. The vapor side will be lower. Which way will the water flow? This is for your beaker example, your analogy. It's just an analogy. We're not talking about actual water. So not talking about the water that's in this equation, just the analogy, the drawn beaker with water in it. Okay, this side is lower. This side is higher. Okay, so water level, your level in your beaker. This side is higher. This side is lower. Which way is the water going to flow? High, reactants are high, products are low. It's going to shift to the right. So your forward reaction will happen faster than your reverse reaction. Water and energy will be converted into vapor faster than vapor will be converted into water and energy. Again, write down those words, what I'm saying, write it down if you need to. Water and energy will be converted to vapor faster than vapor will be converted to water and energy. Forward reaction is happening faster. Next example. A closed container of N2O4 and NO2 are at equilibrium and the pressures increase. So now we're talking about pressure. But if you notice in here, there is nothing, there are no words, nothing in here that has anything to do with pressure. Energy, if you see the word temperature, if you're increasing your temperature, if you were adding more energy, more joules or anything like that, that would affect the energy. Or you would have to see something like the N2O4 or the NO2, the molecules. But we don't see anything as far as pressure here. Okay? So what happens here? The equilibrium of the system shifts to the left to lower the pressure because there are fewer molecules of gas on that side of the equation. Okay, so in this case, what you're going to have to do is you're going to have to count up your moles of gas. Moles are represented by the number that is in front of the molecule. And again, it says gas, gas, gas. If you have something in here that's a solid, you don't count. You don't count it. If you have a liquid, if it says liquid, LL, you don't count it. You're looking for your gas molecules. There is no number on the reactant side. So over here on the reactant side, the only thing I have with a gas, that's a gas, is this. No number in front of it means there's one. So reactants, there is 1 mole of gas. On the product side, there's a gas. 2 moles of gas. Okay? When pressure is involved, your equilibrium, the equation is going to shift towards the side with fewer moles of gas. 1 mole of gas here, 2 moles of gas here. There are fewer moles here. This is when pressure is increased. When pressure goes up, okay, equilibrium shifts towards the side with fewer moles of gas. 2 moles here, 1 mole here. It's going to shift to the left. The opposite of that, if pressure is decreased, if pressure decreases, and you may want to write this down, so write down these 2 things. If pressure increases, equilibrium will shift to the side with less moles of gas. Less moles of gas. When pressure is decreased, when pressure goes down, equilibrium will shift to the side with more moles of gas. More moles of gas. All right, that covers it for notes. There is a video, a YouTube video at the end of this slide that you can go back and watch. I will put the slide in Google Classroom Actually, I will put the YouTube video in Google Classroom for you to go back and watch. That's the end of this video, and then I will be covering the worksheet or giving you a few examples to show you how to get it started.